Hello everyone and welcome back. In this video, we're going to learn about the second technique that can be used to apply bolt pretension in ABAQUS. In the previous video, we learned how to apply using the bolt pretension section, which is the standard way to do it. And now we are going to learn how to do that using the translator connector. And this video is related to this blog post from my blog Learn FEA. So in the previous video, we learned about the first technique using the pretension section. And now we are going to learn how to do that using the translator connector. Okay, so firstly, we need to create a coupling for the nut. And then we should also create a coupling for the bolt near the region where the nut is in contact with the bolt. And just one important observation. For this technique, we should not have a tight contact between nut and bolt. And we should also adjust the coupling's reference node position. So each coupling will have a reference node. Both nodes should be positioned in the bolt axis. The node related to the nut coupling should be to the right. So let's imagine that the bolt head is here to the right, and the nut reference node should be to the right, and the bolt reference node should be to the left. And I'm going to explain why shortly. And then after that, we can create the translator connector between these two reference nodes. And then we can apply the connector load. And then we are going to have something like this. The bolt is going to enter the nut. All right, so let's see how we are going to do this. So here I have the module that we have used before. Before anything, I want to save it. So go to File, Save As, and here I have our working folder. And I'm going to name it as bolt pretension section because we have used the pretension section technique here. Click on OK. And now I also want to, actually, let's go back to load manager. And we have this bolt pretension load created. And I want to delete it. Click on delete. Okay. And also I want to delete this surface. And to do that, here in assembly, we have this surface that was generated. Right click on it and delete. Yes. And I wanted to delete this partition too. So this partition was automatically generated when we created the bolt pretension load. To delete it, let's go to module part, select bolt here, and delete feature, select this rectangle and middle mouse button. Select it again, looks like it didn't work, done. Oh, okay to delete the selected feature, yes. All right. Now we don't have that partition. Probably I lost the mesh, so double click on mesh and then seed part, apply, and mesh part, yes. Okay. Now, before I forget, let's get here on interaction module, go to constraint manager. And you see that we have this tie contact between bolt and nut. Let's delete it. So select it and delete. Yes. Okay. Okay, now we have our module ready. And the first thing I want to do is to create the nut coupling. And this coupling should be attached to all nodes that are part of this inner surface here of the nut. Okay, so select, let me actually go to, yeah, select this nut, right click, or actually select the bolt, right click and hide instance. Rotate the view and let me see one thing here. Yeah. Okay. Actually also hide the bracket, hide instance. Yep. Now go to interaction module, and then we have here create constraint coupling, and I'm going to name it as nut coupling. Click on continue, and then it says select the constraint control points. So I didn't create the reference point, so click on ask, and then click on RP, and let's create the reference point right here. Click on this point, and there we have it. Okay. Now again, go to create constraint coupling, name it as nut coupling. Click on continue, and then select the constraint control point. Now you can select the RP2 zone, and then select the constraint region type surface. Select this surface and click on zone, and we can use the kinematic coupling. This is not a region of a region of interest because we don't have the thread represented here. We also don't have the actual geometry of a nut represented here because a nut doesn't usually look like this. This is simplified, so that's okay to use a kinematic coupling. Click on OK, and there we have it. So all nodes that are part of this surface is attached to this reference point through this kinematic coupling, and which means that anything that we do to these reference points is going to be transmitted to these nodes on this surface right here. Okay, next step is to create the bolt coupling. Okay, let's do it. So now click on nut here in instances and hide. Click on bolt and show. Okay, now I need to create a coupling with a surface in this region. And to do that, one way is by creating a partition here where I want to create the coupling. So let's do this. Go to part, select bolt, and let's create it here. Let's create a partition here. So partition cell, let's see the options that we have. Extend, extrude. Okay, could be this one. Define cutting plane. I want to partition this cell, so select it. Click on done. Okay. Okay, before we do that, we should have at least one point here or where we want to partition. So let's do that. Click on create datum point. Oh, not really this one. Could be this one. Offset from point. Yeah. So right click on create datum point, hold, and then select this option, offset from point, and then click on this point, and I want to offset it in the Y direction. So I should have here the Y to be equal to 5, for example, 5 millimeters where the nut starts. Click on OK, and now we have this point created. and I want to create another one. So click on it, and I want to create one offset of 10 millimeters in the y direction, which is the length of the net. Okay. I also, let me think. I also want to create one right in the middle to be my reference point. To do that, click on this point here right in the middle and offset it in the y direction by maybe, okay, 5 and here 10. So it should be 15 to be right in the middle, 15 mm. Okay, now you see that it was created. I guess this is not right. Okay, so 15, no, it's not 15. I'm sorry. Let's do it again. Go to part, features, and we have this last datum point created, delete it. Yes. And click on offset from point again, select this one. And here we have 15, 5, and then we can have it as 10. Okay, now we have this point here, it's okay. Yeah. Actually, a better way to do it, let's delete this datum point. There is a better way to do it. We are going to create this datum point later. Okay, now let's do the partitions that we need to do here. And to do that, go to create partition, select this cell, middle mouse button, and select this option, point and normal, and select this point and this edge to be our normal, and then create partition. So it's going to create a partition that passes through this point and that is normal to the edge we selected. And this is the result. Let's do it again. Create, click on done. And now let's do it again. Now clicking on this point, actually this section, this partition, middle mouse button, point and normal, select this point and this edge, create partition, done. Okay, so now we have it. Now double click on mesh, seed, apply, okay, and mesh part, yes. Now let's go to interaction interaction module, and let's create you see that we have this reference point 2 that was used for the nut coupling, and I mentioned here in this blog post that the nut couplings reference node should be, if we have the bolt head here, it should be near to the bolt head. Okay, so here we have the bolt head, and here we have RP2. That means that the bolt reference node should be to the right here in this image. Okay, so let's do that. Click on create datum point, offset from point, select the RP2, and I want to offset it to the right. So it should be in the positive X direction. So let's define here as, here I mentioned that these 2 points need to be of distance from each other by a small distance, such as 2 millimeters. So let's do it. Define here the offset in the X direction as 2, and then press enter. And you see that we have the new point created. Click on RP and click on this point that was created. And then now we have our RP3. Okay, now click on create constraint And now we have the bolt coupling. This is a coupling, continue. Select the constraint control point, should be RP3. Yeah, should be, press ESC and again, bolt coupling. Click on continue, select RP, let me zoom in and select RP3. Done. Click on surface and select this surface. Done. Should be kinematic and click on OK. And now we have it created, even though we cannot see it here. To be able to see it, we can go to Constraint Manager and we have the bolt coupling. And you can see that it was created here. Okay. Now, next step is to create the translator connector. To do that, click on Connector Builder on Interaction Module. Connector Builder. And we can, so it says select the first connector point. We can select RP2 or RP3, it doesn't matter. Let's select RP2, for example, and then select the second connector point. It's gonna be RP3. Okay, so now we have 0.1 RP2, 0.2 RP3, and also a wire is generated between these 2 points. And here we have a section that is not defined, so we should define a section. Click on it, create section, and let me name it as translator connector section. And here I want to get basic category, and here in translational type I should select wait, it's here actually. In connection category I should go to assembled complex and here select translator. Okay, so for this type of connector we have just 1 degree of freedom, that is displacement along the x direction. And the x direction is actually related to a local coordinate system that is automatically created for this connector. And I'm going to explain shortly how this coordinate system is created. Let's just now define here the behavior properties of this connector. And here we don't need to define anything actually. We can click on OK. And now we have this section created. Now the software knows that the connector that we want to create is a translator connector. And here in this blog post, I explain about how this connector works. And basically, it fixes all degrees of freedom, but the one related to the x-axis. And the x-axis is created, so you see here, CSYS1, that is coordinate system for node 1. That is the first node we clicked, that is RP2. It's going to create a coordinate system on axes between points. And this line connecting the 2 points is going to be axis 1, that is the x-axis. Okay? So basically, the origin of this coordinate system is going to be at RP2, and the x-axis is going to be directed from RP2 to RP3. And this is the only degree of freedom for this type of connector, which means that these nodes can only move in the axial direction, the x-axis direction. It cannot move in the y, z, or rotate about x, y, and z. Okay? So for that reason, we don't need a tie contact between the nut and bolt, because the movement will be controlled by this connector completely, the nut will be able to only move in the axial bolt direction. Okay, we can click on OK, and you see that the local coordinate system was generated. You see that the x-axis is from RP2 to RP3. Okay. Now, the next and last thing we should do is here on load step. Let's go to module, load, and I want to apply a connector load to this connector that we just created. And to do that, click on create load, and I'm going to name it as connector load. And it's going to be applied at the load step. And let's find here connector force. Click on continue. Select wires, attachment lines, or click done to use assembled fasteners. So click on this wire that was generated when we created the connector, and then click on done. And then here we can only define force in one direction, that is the direction of the x-axis, which is the only degree of freedom we have for this connector. So there is one very important rule here for the sign of this force. If we apply a positive load of 50,000 Newton, just as before, this is considered to be a tractive load for the connector, which means that this force will tend to separate the nodes from each other. It's like we are putting the RP3 to the right and the RP2 to the left. And if we apply a negative load, the opposite will happen. The nodes will try to move towards each other. It's like a compressive load. And this is only true if we have the local coordinate system with the x-axis from RP2 to RP3. If we had inverted the direction of the x-axis, then this rule will not be true. It will be the opposite. A positive load will mean compression, and a negative load will mean traction. Okay, but when we create the connector, automatically the x-axis is from the first to the second node. Then this rule of positive equals traction and negative equals compression is true. Okay, I'm telling you this because many people use ENSA or HyperMesh to model connectors and to actually set up the model. And in there, we should create the coordinate system manually. And if we create this coordinate system with the x-axis to the left, then we should be aware that positive will mean compression. Okay. All right, so let's define it as 50,000. And let's remember that RP3 is related to the coupling connected to the bolt, and RP2 is connected to the nut. If we apply a positive load, and this load tries to separate these two nodes, that means that RP3 is going to be forced to the right. And since RP3 is connected to the bolt, it's gonna try to move the bolt to the right. And RP2 is going to be pushed to the left. And that means that the nut is going to be forced to enter the bolt. And you can see here in this animation, this happening. Okay. Notice that we have movement only in the axial direction of the bolt. This connector does not allow movement in the Y, Z, or rotation about X, Y, and Z. Okay, The only movement that we can have is the one shown here in this image. All right. Now we have everything ready, I think. Let's show the bracket, show the nut. Let's go to job, and I want to create a new job. So click on create, and this one is going to be named as translator connector. Continue, accept the standard configuration, and then submit it. Click on monitor. And let's wait it to finish running. Okay, so this is running with no, it had some difficulties to run the first sub-step, but then it started to converge easily. Okay, it's almost finished. Okay, now it's finished. Let's close this window, and now you see that this is completed. We can click on results to post-process it, rotate the view, and let's see the deformed shape. That's what we have. Okay, something very similar to what we had before for the bolt pretension. But notice that we don't have the bolt pretension section. We don't have that the nodes moving here. We don't have that that effect here in the bolt section. What's happening here? Let's animate it. You see that what is actually happening here is that the bolt is moving in the direction of the bolt head. Okay, and I like this technique because this is what happened in reality. We assemble the nut to the bolt, and we move the nut towards the bolt head. So the force comes from the nut actually when we apply the bolt pretension in reality. So that's why I like more this strategy. Okay, and I also think it's simpler when we are working with larger modules, because when we have larger modules, we may have many bolts, and we can do it for each bolt connection and then create a set of all connectors and apply only one bolt pretension for all connectors, for that set of connectors. Okay. All right, so we can also plot von Mises stress and analyze and post-process the model and analyze the stress levels and everything, but this is not the purpose of this video. All right, I think that's it. Don't forget to read this blog post. Here we have much more detailed information with respect to the theory involved for the in these two techniques. You see that here we also have this animation for considering bolt pretension sections. So you see that the nodes from one side of the section is moving in a way that it decreases the bolt length, and then it yields to a bolt pretension load. Okay, so don't forget to read it. All right, thank you for watching. I hope you liked it, and see you in the next video.